Hey everybody, it turns out I can insert a little video of my face. So here we are. But on the other hand, I think you guys have all seen me and it's still me. So I'm going to turn this video off and go back to the usual pencil with a voice mode. Thanks. Hi everyone, we're solving quiz 5.10 today. The solution appears in the next slide. But somebody on Piazza said, well, it's kind of a confusing solution. I don't understand it. And and the answer is unless you kind of see what the structure in the problem is, it is indeed a confusing solution. So let's work it out here in an explain everything video. Near the end of lecture 19, I made a comment that a lot of these problems with calculating probabilities over multiple random variables, they can be solved if you somehow have special structure in the problem. And in fact, this quiz is like that. There's a special structure to the four random variables, y1 through y4, that if you see the structure, then the solution becomes fairly straightforward. So to see this structure, let's solve a simpler problem. Let's solve this problem. Y1 and Y2 of joint PDF FY1, Y2, Y1, Y2 equal to 2 for 0 less than or equal to Y1 less than or equal to Y2 less than or equal to 1 and 0 otherwise. And let's find P of C equal to the probability that the max over yi for I equals 1, 2 is less than or equal to a half. So this simpler problem is solvable, mostly because we only have two random variables. And now we can draw a two-dimensional plane and identify the region where the joint PDF is non-zero and identify the region where both random variables is less than or equal to a half. So we start by drawing the two-dimensional plane as a function of y1 and y2. We identify the line where y1 equals y2, and then we observe that there's this upper triangular region, and in this triangle we have y1 greater than or equal to y2, and of course we have our corner points 0, 1, and 1, and so this triangular region is exactly where the joint PDF of y1 and y2 is equal to 2, and outside this region, the PDF is 0. The next step is to recall that the maximum of two random variables is less than something if and only if each of the random variables is less than that something. In this context, the probability the max is less than or equal to a half is the same as the event that the probability y1 is less than or equal to a half and y2 is less than or equal to a half. And this region we can draw on the xy plane in the following way. So it's everything in this lower left corner where y1 is less than or equal to a half. You're to the left of the vertical line, and y2 is less than or equal to a half, meaning you're below the horizontal line. The next step is to express this probability as an integral over the region of the joint PDF. So this is a correct integral, and it's the correct integral for any joint PDF of y1 or y2. It's an integral over the blue box region to the lower left. The next step is to specialize this integral to the joint PDF that we're given, namely that the joint PDF is 2 for y1 between greater than 0 and less than y2 and less than or equal to 1. It's only 2, we're specializing to the PDF that's the non-zero in the triangle region. And what that corresponds to is doing the integrating the joint PDF over this region. So this is equal to um, y1 goes from 0 to 1/2, and then y2 goes from y1 because it starts along this line where y2 equals y1 up to 1/2. We have to get our pencil back. Right, and then we have the joint PDF in that region, dy2, dy1, 0 to 1/2, and this will be 2, 1/2 minus y1, dy1, and this equals y1 minus y1 squared, 0 to 1/2, which is equal to 1/2 minus 1/2 squared minus 0 squared, and that's a 1/4. So we solve this problem using the definitions, and but in fact the calculus steps weren't really necessary. In fact, P of C is equal to the density, which is equal to 2 times the area of the blue triangle. And so we have this is 2 times 1/2 the base times the height, and the base is width 1/2, and the height is 1/2. And so this is 2 divided by 8, and we get 1/4. Exactly the same answer we got with calculus, but when a PDF is uniform over some region, we can use a geometry calculation instead. So now we're ready to go back and solve our original problem where we had a 4-variable PDF of y1, y2, y3, y4, and this was equal to 4 for 0 less than or equal to y1, less than or equal to y, less than or equal to 1, and 0 less than or equal to y3, less than or equal to y4, less than or equal to 1, and 0 otherwise. And the problem we're solving is more or less the same. It's the probability that the max over the yi's is less than or equal to 1/2. But this is a 4-variable PDF, and it's hard to visualize or draw the 4-dimensional space. So let's start with the basic probability fact that this probability is still the probability y1 is less than or equal to 1/2, and y2 is less than or equal to 1/2, and y3 is less than or equal to 1/2, and y4 is less than or equal to 1/2. And now one approach from here is to just simply look at this PDF really hard and stare at it, and then write the appropriate limits of integration because you're kind of just good at understanding what these two sets of constraints, this set for y1 and y2, and this set for y3 and y4 represent. And if you do that, you get the solution that is on the final slide that's straight from the solution manual for the quizzes. However, the reason we're making that video is that that leap to simply writing down the calculus region of integration is not so obvious to maybe to most people here. In fact, the solution is obvious to people who see what is the inherent and maybe you might say hidden structure in their problem. It's that we have a pair of constraints where y1 is less than or equal to y2, and then a separate constraint where y3 is less than or equal to y4. And in fact, what you have is a kind of independence between pairs of random variables. And what we mean by that is that we can write the PDF we wrote before for y1 and y2 in solving the previous simpler problem. And we can write a similar PDF for y3 and y4. And then if you look at these two definitions, you realize that you can write, oh, there's a little mistake here. The joint PDF of y1 and y2 and y3 and y4, you can write it as the product of these two PDFs, a joint PDF for y1 and y2 times a joint PDF for y3 and y4. So looking at my work, I see I left out a little y3, y4 here. But in fact, modulo that correction, you can see that the joint PDF of the four random variables factors into a PDF for y1 and y2, and then a PDF of y3 and y4. So if you read this section 5.10 of the book carefully, you would know that we would say that f of y1, y2, y1, y2, and f of y3, y4 are versions of marginal PDFs. And in fact, what the above formula is saying is that this joint PDF is a product of marginal PDFs. And in fact, what's happening here, and we haven't developed this idea very much, is that the pair y1, y2 is independent of the pair y3, y4. Once you see this independence, you realize that the event P of C, the probability that y1 is less than a half, y2 is less than a half, y3 is less than a half, and y4 is less than a half, right, can be factored into kind of two independent events. The one independent event is that y1 and y2 are less than a half, and the second independent event is that y3 and y4 are both less than or equal to half. So this is probably y1 is less than or equal to y2, less than equal to half. And the probability y3 is less than equal to y4 is less than equal to half. And then we realize that, oh, this problem we already solved in the previous slide. It was the simpler problem with two random variables, and we found the answer was 1/4. And this problem is in fact exactly identical to the y1, y2 problem because y3 and y4 have a PDF which is identical to the PDF for y1 and y2. It's equal to 2 over an upper triangular region on the y3, y4 plane. So in fact, uh, this probability is equal to 1/4, and the answer is 1/16. So if you go and look ahead at the official solution in the quiz solutions, the official solution simply wrote an integral that kind of looks like this. It was the integral over y1 from 0 to 1/2, and the integral over y2 from y1 to 1/2, and then the integral over y3 from 0 to 1/2, and the integral over y4 from y3 to 1/2, and then the joint PDF over the region 4, and now this will be dy4, dy3, dy2, dy1. And if you remember that this is the integral over y1, and this is over y2, and this is over y3, and this is over y4, we can factor this integral 0 1/2, y1 to 1/2, dy2, dy1, 0 1/2, y3 to 1/2, dy4, dy3, and if you do the steps, this will also give you the 1/16. The thing to remember though is that exactly what allowed you to set up these regions, doing and then to recognize that those regions can be factored, particularly this recognition of the factorization, it's really telling you that there's this kind of independence of this joint PDF into a y1, y2 pair that's independent of a y3, y4 pair. It's exactly what I mean where I say earlier that, oh, if the problem has some hidden special structure, you'll be able to do these calculations. But in fact, you kind of have to recognize what the structure is in order to understand how to set up the calculation and do something reasonable. And finally, looking at the official solution, it's worth noting that the calculus here was done differently than it was done on the very first slide. So this integral in the box, right, corresponded to the integral we did on the very first slide, where we had a joint PDF of y1 and y2, and we found the probability that here is 1/2, here is 1/2, 1, 1. We found the probability of being in this box, in this triangle. In particular, the area of that blue triangle is exactly the calculation that goes on in this double integral. And what we did here was that we wrote this integral dy1, where we integrated y1 from 0 up to y2, up to the line where y1 equals y2, and then we integrated y2 from 0 up to a half, right? And the answer we got was equal to 0 to 1 half dy2 times y2, and this is equal to 1 half y2 squared, 0 to a half, and this is equal to 1/8. So if you check back on the first slide of this problem, on the first slide, we set up this integral the opposite way. We integrated y1 from 0 to a half. And then we integrated y2 from y1 to 1 half. That corresponds to doing this integral over this green slice. And then we did a bunch more steps, but eventually, if you do that, you'll get the same answer, 1/8. And of course, uh, that's the area calculation, but each one of the marginal PDFs for y1 and y2 and y3 and y4, this factor of 4 was two factors of 2, and there would have been a multiplier of 2 in here to give you the answer 1/4. This discussion here is just about the calculus of setting up the integration over triangular regions, and just a reminder that when you're doing this, there's always one way that's the simpler way, where the calculations are a little less work, and that's good to keep in mind.